Hello everyone. Today I'm gonna talk about one of the most important modern physics experiment called double slit experiment, and then that shows the light is a wave, as I talked last time. And then as I talked last time, wave is one of the most important property is a diffraction. So if the light is a wave, then it will show us the diffraction as well. So the physical situation here is the same. We have a small hole here, right? And then because of the light is a wave, it will spread out, right? So that is called diffraction. So our actual experiment is called the double slit experiment that shows two important property of the wave. The first one, diffraction, and the second one, superposition, interference that you learned from the sound source, right? So then now we have a two light sources passing through the two, slit, and then you see they will spread out, meaning that it's a diffraction. And then you will see also have a, bright dark area, which means like a sound wave, you have a clear sound, sound cancel out, nothing here. So like the sound wave, light wave is also interference. So that means you have at some point you have a maximum, at some point you have a minimum the light intensity. So the basic idea here is the same. You have you know, first light is passing through, and then the second light is passing through the second slit, and then you see it's R1 and R2, and sometimes you have a bright area, and then again sometimes you have a dark area. Again, in order to have a constructive interference where you have a bright area, and then that is what we focus on, path length differences, right, of two lights, right? So if you can calculate path length differences between this R1 and R2 as we did for the sound wave, right? So you can see obviously here R2 travels longer distance than R1, right? So then if you can find again the path length differences, we can see where we have a constructive wave, where we have a destructive waves, right? So then everything is exactly what I explained. You can check and read the textbook carefully again. But this is a main idea here. Okay, so this picture shows you, I can go back to the previous slide again. But the thing is, this is a path length 1, and then this is a path length 2. And then you will see this is the path length differences. So we assume this is a angle theta. So then now you see this is a theta 90 minus theta. Then you see this is a theta again. So then you can say this is a hypotenuse. This is nothing but right triangle whose hypotenuse is a slit spacing d, and then angle theta. So now you can see this path length difference is a d sine theta. And then especially when these path length differences is a m lambda, as we did for sound source, then now you see, okay, then this is a constructive wave conditions, right? So then thing is again, this is a d sine theta is path length differences, and then when this is a m times a whole number times a wavelengths, then you see this is a location where we have a constructive wave. And of course, m can be 0, 1, 2, 3. If m is 0, what does that mean? Two light travel same distance. So that means path length difference is 0. So that's the location where you have a center maximum. Because in other words, R1, R2 travels the same distance, so path length difference is a 0 for this case, right? Okay. And then another condition we have is the slit here. So there's basically we have our screen here, And make sure this spacing d is much shorter than the distance between the slit and the screen. So L is much larger than D. And then we can also find the relationship between this Y, which is the location of the maximum point we have. So that means, okay, we have a maximum here, we have another maximum here, and then now we define this distance is Y. And then now you see this is angle theta, and then this the distance between two, the slit and then screen is L, and then you see tan theta, tangent theta is a Y over L, right? So this is just two conditions you gotta remember for this double slit experiment. It seems very complicated, but it's extremely simple if you understand interference of you know sound sources. So now we have two conditions. If I redraw it, let me redraw the picture again. So especially again, the slit distance is extremely small, just a few millimeter, even less than few millimeter. While the distance from here to the screen is much longer, which is in general like a meter scale, 1 meter, 2 meters. So basically, even though you have a D here, you can assume this is a location where you have a double slit. It's just point. And then far, far away, you have a screen. And then if you are interested in a specific location of a maximum interference, then you now draw this, and then this is a theta, and the distance from here to here is L, and then this is your Y. So again, you have a tan theta is Y over L, right? And then another requirement for the constructive wave here, if you remember, path length differences is a D, sine theta is a M lambda. So this is two equation, the core equation for double slit experiment. So make sure you can drive these two equation, right? And then next tab is a straightforward, right? So then, from the d sine theta is m lambda, I move d here. So then you can see sine theta is m lambda over d, but make sure theta is not a single value, right? Depending on which maximum value you here, right? This is angle theta 0, this is angle theta 1, angle theta 2, and the line from here to here, 5, 6, 7. So your theta is changing, right? So you can have any infinite number of basically theta here, right? So m can be 0, 1, 2, 3. So that means theta 0, theta 1, theta 2, right? And then another thing is you remember another tangent theta we just drive is what? Y over L. And then here we will use a mathematical techniques called small angle approximation, which is sine theta and cosine, tangent theta, sine theta and tan theta is approximately theta when the theta is small. For example, let's assume, you know, sine pi over 6 over pi. Pi over 6. Everybody knows sine pi over 6 is what? 30 degrees, right? Which is a 1/2. And let's see if that makes sense. What is the sine pi over 6 is what? Approximately, if we use this small angle approximation, sine pi over 6 is a roughly pi over 6. But now you know pi is a 3 point something, so then you can say this is 1/2 roughly. So then you see this one works, right? So then now you see sine tangent theta and the sine theta is gonna be the same, especially the angle is small. Then you can say y over L is a m lambda over d. So in other words, ym over L is a m times lambda over d. So if you multiply L both sides, you will see y m is going to be m lambda L over d. So this is actually the height of the maximum position, right? Of course, m is a 0, 1, 2, 3. So this is a, these three equation, this one and this one and this one is for, double slit experiment. But again, you don't need to memorize anything, right? Just to, start from here and then think about why we have this one. Think about why we have this one, right? Basically, we have this equation because of this picture, right? Tangent is L over Y, Y over L. And the sine thing is from path length difference is equation from this slide, right? That's why you have a d sine theta as m lambda, right? So then, combining these two will give you this y m, right? And then you can also find the distance between two maximum points. So that is simply ym plus 1 minus ym. So ym plus 1 is everything same except ym plus 1. So you change m part, m plus 1, and then this is a m lambda L over d. So then you will see cancel, delta y is a lambda L over d. So this is the distance between two spacing of a maximum, bright area. Right? So then now, I'm gonna go, drive this one again, because this is the most important thing, right? So the path length differences between two light is t sine theta equals what? M lambda. This is for maximum bright area condition. And then now you know that tangent theta m is also what? Y over L. So then now if you change this one, sine theta m is m lambda over d, and then this is you can approximate this two equation using small angle approximation, where sine theta m is tan theta m is theta m is what? M lambda over d equals y over L. So then now you see y is m lambda L over d, right? So make sure you can drive these things, right? And then the problem is simple. I'm not going to ask you, using this formula, the number given, boom, boom, boom. No, that's not physics, right? So you make sure you know how to drive these things, right? So for this question, lambda is a 633 nanometer. So now you know what the lambda is, right? And then slit space the 0.4 millimeter. So you know these are 0.4 millimeter. Okay, of course, you have to convert everything to meters, right? And then the viewing screen is a 2 meter. So then it is a 2. So three numbers are given. At bright fringe is observed 9.5 millimeter. So that means your y is 9.5 millimeter. So then asking m. So that's a piece of cake, right? So I believe everybody now can solve m, right? And the next one is similar thing, but the next condition is a destructive interference, but everything is the same, except what? Your path length difference is what? M plus 1/2 times lambda, right? But in general, we are interested in, constructive wave position only, right? So this is a condition for destructive wave. This is condition for constructive wave, right? And again, double slit experiment, you see the first one is the M0, M1, M2. Then we'll have a lambda, Y1 here, Y2 here, Y3 here, Y4 here. Of course, here path length difference is 0. And then here, the destructive wave path length difference is lambda over 2. And again, you have a constructive wave path length difference is lambda, right? Again, another half lambda, half lambda, half lambda, half lambda. Then you have a bright, dark, bright, dark, bright. Okay. And then, of course, you have a maximum central intensity. So this is kind of the brightest area, compared with this the second one. Is a slightly brighter than this one, right? And again, we have a few questions. Again, now you can quickly do it, right? D sine theta is a m lambda. So that means the sine theta is a m lambda over t. And then this is the same as a tangent theta, which is a y over L. So this is again your formula, right? So then now you can solve, right? Double slit experiment. The point on screen where the dot show how far from the left slit and from the right slit. So now this is a central, and then 1 lambda, 2 lambda difference is here, right? So then answer is C. And again, experiment of a double slit interference pattern, right? The screen is moved far away from the slit. So then what does that mean? From this equation, you increase the L, right? That's what it means, right? The screen is moved farther away. The fringe will be closer together. So now you're investigating y as a function, delta y as a function of a L, right? So then now you see your y is gonna be m lambda L over t. So if you increase L, y will be increased as well, right? So that means the distance is a further apart, right? And then same question, similar question, right? If the double slit experiment again, the green is used. The green in general is about 500 nanometer. Maybe I'm wrong, but somewhere there. Right? With everything else the same, the bright fringe will be. So the initially we had a red one. Red has a 800 nanometer. So we change its wavelength from 800 to something, less than 800. Again, we come back here. Sorry, here, right? So now we change the lambda, decrease. Then y will decrease as well, right? So the answer is closer together, right? And another question, slits are moved closer together. So now we change D, right? Then what will happen? If you change D, D gets smaller because this is the numerator, y will increase, right? Okay. Y will increase further apart, right? And then similar example, slit again. I'm gonna do it again one more time. Sine theta is a m lambda, right? So this sine theta, right? So the sine theta is a m lambda over t. This is the same as a y over L, right? So this is a tan theta. This is a sine theta, right? So again, you have this formula. And then slit distance 0.04, so d is given. And then lambda 699. So what is the angle of the first? So now you're looking for the angle theta, right? What is the, and then m is 1. So m is 1, lambda given, d given, then this value itself is gotta be your theta, right? Okay, so that's not bad, right? So simple question again. And then what is the angle of the 30s? So then now you have a m is a 30, lambda given, d given, and then you change the theta here, right? So theta will be given, right? So you can find it. Okay, so this is a first topic of the chapter 17, and then we'll have another experiment called the single slit experiment the next class, and that's going to be the end of the chapter 17. And let me know if you have any question. You can send me an email or I have a question via Canvas. Thank you.